Good afternoon, everyone, and during lecture number 8, I will talk about experimental results on absorption and emission of light by semiconductor nanocrystals. And let's start with the history. In the early 1980s, Akimov and Danushenko, and parallel to them, Bruce and his co-workers, published pioneering articles in which physical manifestation of the quantum size effect was demonstrated. And the main method to obtain this was size-dependent absorption spectroscopy, and the first object of the investigation that helped to demonstrate it was a copper chloride crystal inside of the glass matrix. I remind you several facts about copper chloride crystals. First of all, the exciton Bohr radius is about 7 angstrom. The crystal lattice of the copper chloride is about 5 angstrom, so it's almost the same as the exciton Bohr radius. Copper chloride nanocrystals usually possess weak confinement limit. It means that for most cases, their mean radius is more than exciton Bohr radius. Copper chloride crystals also possess very big exciton Rydberg energy. This means that we can see exciton resonance in the absorption spectra, even at room temperatures. So, let's go to the absorption spectra of the copper chloride crystals inside of the glass with a mean radius of 15 nanometers. It is usually said that copper chloride nanocrystals of such radius possess optical properties almost the same as the bulk crystals or monocrystals. The absorption spectra possess two intense absorption bands, which are called Z3 and Z12 exciton absorption bands. These bands are relevant to different valence subbands. Here the branches number 1 and number 2 in the valence band are degenerate at 0 point. That's why they provide only one absorption peak instead of the two. This is the flat interband absorption. This is the absorption of the glass matrix. When we decrease the size of the nanocrystals in size of the glass matrix, we have the very monotonous shift of the first absorption maximum towards bigger energies or smaller wavelengths due to special confinement of excitons inside of the crystals. Also, we can see here that with decreasing the size of the nanocrystals, the width of the first absorption band maximum increases. This is more than this one. Particle in the box problem predicts this ratio between energy and the mean size of the crystals. If we go to their experimental points in this axis, we see that they are very close to this ratio. But if we are talking about more precisely description of the experimental results, we will go to the Lifshitz laws of asymptotic distribution, which state for diffusion limited growth. And diffusion limited growth is the case of the copper chloride crystals inside of the glass matrix. The difference between this formula and the formula that I have showed you before in previous lectures is this constant coefficient. During several years, different scientific groups in different parts of the world obtained very strange results. They see that the difference between experimental points and the line obtained by the theory were differed only by some constant value, and this value was 0.62, and that's why now we use this semi-empirical modification of the Lifshitz closure function to calculate the dependence between energy and the mean size of the crystal. However, in the case of the finite size distribution, the experimental peak position differs by a constant coefficient all the time, comparing with the theory. And now this formula we can use while fitting the size dependence of the position of the Z free exciton absorption band. But what about crystals of the second, sixth type? These nanocrystals were obtained in numerous matrices, in inorganic glasses, inorganic polymers, and in various solvents. This type of crystals includes very widely known cadmium sulfate and cadmium selenide crystals as well. And they are very famous and very widely used in the case when they are providing strong confinement regime. It means that the mean size of the crystals is less than the exciton Bohr radius. Here we can see the absorption spectra of the mixed cadmium sulfate selenide nanocrystals inside of the glass matrix. We can see from the picture that this absorption spectra differs drastically from the absorption spectra of the monocrystal of cadmium sulfate or cadmium selenide, because I remind you that the absorption spectra of monocrystal or bulk crystal is always flat and structureless, especially at room temperature. But here we have, for example, curve number 1. It possesses about 3 different absorption maximus. What about other curves? They possess at least 2 absorption maximus. With the decreasing of the size of the mean size of crystals inside of the glass, the shift of the absorption band towards smaller wavelengths can be observed. If we are talking about crystals with a mean size of about 2 nanometers, the difference between the energy position of the first exciton absorption band of the small nanocrystal and the position of the first absorption maximum of the bulk monocrystal will be about 0.3 electron volts. But the exciton Rydberg energy of the cadmium sulfate is about 16 millielectron volt, and for cadmium selenide is 30 millielectron volt. It's 10 times less than the shift of the absorption band. It proves that these crystals provide strong confinement regime. It means the kinetic energy of the confined electron in the hole are much greater than the exciton Rydberg energy. It also should be mentioned that these absorption spectra of these glasses are very alike to the absorption spectra of the commercial glasses that are used as color cutoff filters for visible spectrum. Here we have that the absorption spectra of the glass number 1, and really by the naked eye it will look like light red color filter. Glasses number 2 and number 3 will look like orange color filters, and glass number 4 will look like yellow color cutoff filter. So it means that the quantum size effect can help us to provide to create technology for commercial uses. And here to synthesize 4 different cutoff color filters, we can use only one chemical composition of the bars, but 4 different heat treatment regimes. This is how quantum mechanics help to solve different technological problems. But what if this type of crystals will grow very big in size? So in that case, their mean size will be larger than exciton Bohr radius, and it means they will provide weak confinement regime. If you look on the absorption spectrum of the crystal with the mean radius of about 9 nanometers, we will see that it is a hydrogen-like exciton spectra. So it provides bulk-like exciton bands featuring a small shift with size in accordance to the weak confinement limit. What I want to tell you about this type of crystals. 2,6 compounds provide evidence for the smooth evolution of the fundamental absorption spectra from crystal-like to cluster-like properties via weak, intermediate, and strong confinement regimes. Another interesting example is lead iodide crystals. Lead iodide is an interesting example of the so-called Acceptorlike electron, which is characterized by an electron localized at the center of the spherical crystallite and the whole experiencing a confined motion. Usually they are corresponding to the intermediate confinement range, where the mean size of the nanocrystal possesses this ratio. Here also we have electron effective mass is much larger than the effective mass of the whole. The localization of the heavier electron occurs because of the potential of the whole, whose motion is confined by the boundaries of the crystallite. Experimental points shown here shows a nice correspondence with the theoretical line developed within the framework of the effective mass approach for the Acceptorlike exciton model. How spectrally selective methods can be used for investigating properties of the inhomogeneously broadened mirrors, for example, glasses with the nanocrystals inside of them. According to the theory of the absorption saturation in inhomogeneously broadened systems, the width of the burning hole monotonically grows with rising excitation intensity. We know that the shape of the burnt hole is Lorentzian. You can see it here. So, based on this, we can, using the full width half maximum of the burnt hole, this one, we can calculate the homogeneous broadening of the spectra corresponding to the crystals of the specific size inside of this broadened absorption spectra. So, I'm repeating, this is the full width half maximum value of the burnt hole, and this is the full width half maximum of the homogeneous broadening of the spectra. And see here you also can see the increasing of the hard width half width of the burnt hole depending on the intensity of the optical excitation. But sometimes the shape of the burnt hole spectra is not Lorentzian. Maybe it is Gaussian or even wider, like here. And scientists have found out that the large values of broadening are typical for crystals that were formed during the process of the competitive growth. But in case of the very narrow homogeneous width of the burnt hole inside of the spectra, we are dealing with the crystals that have grown during nucleation stage and normal growth stage. So that's how can we use the spectrally selective spectroscopy in determining the different stages of the crystallite growth. But if we are dealing with the inhomogeneously broadened luminous spectra, we can use selective emission spectroscopy or so-called photoluminescence excitation spectroscopy. On the panel A, you can see a usual absorption spectra of the copper chloride crystals inside of the sodium chloride crystals. This curve corresponds to the dash curve corresponds to the ordinary photoluminescence of the copper chloride crystals, which was obtained under broadband ultraviolet excitation. But if we take several wavelengths from these luminescence spectra and record for every wavelength its own excitation spectrum, we will see that this excitation spectra differs drastically between each other and from the original absorbance spectra. So these experiments revealed a complicated structure of the real absorption spectra and made it possible to identify the number of excited states of Z3 and Z2 1,2 excitons. The identification of sunburns in the excitation spectra led in the conclusion, in this case, that copper chloride crystals have a cubic form instead of the spherical one. So, summarizing this part, we have considered several examples of size-dependent optical absorption spectrum resulting from the quantum confinement effect. In case of the weak confinement range, we can definitely use the effective mass approximation while calculating the experimental results. For smaller crystallites during strong confinement regime, we should also bear in mind not only the effective mass approximation, but the condition of the electron-Coulomb interaction and the finite potential barrier. Moreover, in case of the weak confinement regime, we can obtain the smallest value of the homogeneous broadening of about 0.1 milli-electron volt, but during strong confinement regime, for very small sizes of nanocrystal, the homogeneous broadening of the spectra will be 10 times more, at least 10 times more. In real nanocrystals, again, in real nanocrystals, the deviation of Hall properties from that of the ideal particle is occurred. So it means that we will see the fine structure in the absorption. We should see the fine structure in the absorption band of such crystals, but again, in homogeneous broadening interferes ours, and we can't see the fine structure. That's why the complicated structure of the first absorption feature can be performed by several means. First, by means of nonlinear pump and probe spectroscopy. Second, on the basis of the second derivative analysis of the absorption spectrum. And third, and the most obvious one, by using highly monodisperse ensemble of perfect nanocrystals. Here I show you the results of nonlinear pump and probe technique on the basis of the spectral hole burning inside of the absorption spectra of cadmium selenide nanocrystals in glass. Here we can see that while monotonically tuning the excitation, energy, and wavelength, finally we obtain not one hole burnt in spectra, but two holes simultaneously. The reason for these two bleaching frequencies is the fast relaxation of the exciton from the first excited state to the ground state with a time that is similar to the recombination time. It means that two holes correspond to the two simultaneous effects. First one is recombination, usual process, and second one is the fast relaxation of an exciton from the excited state to the ground state. Tuning of the pump frequency within the band provides the size dependence of the energy separation between the first excited and the ground exciton state. This one. And we can see here the experimental results of these values of the energy separation for cadmium selenide nanocrystals grown in glass, in organic glass, and organic environment. And we can see that both these cases are in good coincidence with the numerical data calculation. The substructure of the absorption spectra also can be elucidated by using second derivative analysis of the absorption spectra. This technique doesn't provide size selective information, and it yields the data relevant to the mean size only. But nevertheless, we still can manifest the fine structure of the spectrum. And here we can see we have vertical lines which show resonances calculated by the means of the effective mass approximation and the corresponding optical transitions here. And the last third technique was about synthesizing the ideal monodisperse ensemble of particles. I was talking about it during previous lectures, so now I won't interfere it. Thank you for your attention and goodbye.